Good day, everyone. Welcome to this webinar hosted by Opti-Num Solutions. Today, we'll be looking at AI in radar. Particularly, we'll be coming at this from people who work a lot with AI, not necessarily radar experts. And we'll be looking at how you can apply AI to this sort of workflow for radar. And this talk is not meant to be exhaustive on applying AI to radar, but really it's meant to plant the seed. So we'll look at some of the benefits of applying AI in radar and also then cover the workflow that you would probably be expected to follow, and then look at some of the tools we use when applying AI to radar systems or any sort of problems in general. A bit about ourselves. We are Opti-Num Solutions, a software and digital engineering consultancy company. We are also the authorized resellers of MathWorks products in the Southern African region. We operate in three main skill sets. This includes your AI modeling, your model operations, and also your simulation engineering. Some of our clients include Lodox, Hensoldt, and CSIR. We operate in a range of industries as well. Those can be seen on the bottom right of this slide. A bit about myself now. I am Dalukolo Hadebe. I'm a graduate engineer within Opti-Num Solutions. I hold a BSc in Aeronautical Engineering from Wits University. And in my time at Opti-Num, I've mainly been working in AI and looking at how AI can be applied to engineered systems and specifically engineering problems. On the agenda today, we'll be looking at some of the applications of radar, the suitability of AI for radar systems. We'll then go on to introduce AI and then cover the AI workflow. I'll then go into a demonstration, and finally, we'll speak about the deployment of AI systems. So firstly, what is radar? Radar stands for radio detection and ranging, and it operates by the principle that you send out radio waves through a medium or to an object, and the reflected waves are then processed. And through the processing of this wave, we can obtain various functionalities. And some of these functionalities in industry include things like your search applications. Using the radar, you're able to find out if something is out there. And then you're also able to classify it based on the radio wave that is returned. We can also pass multiple radio waves over an area, and that lends itself well to then imaging, such as in your synthetic aperture radar applications. We can then also communicate through radar signals by encoding messages into them. We could also track objects, not just search for them. And then we could also assess and protect an area using radar systems because you are able to tell when there's interference based on the returned waves. And then we could also measure weather phenomenon. As radars pass through a medium, we could tell the distance and the speed at which it propagates, and then we could also measure weather phenomenon through that. And so if you think about all these applications of radar in industry, it leads me then to say, radar is actually perfect for AI. And the reason I say this is because AI systems are particularly good at applications that involved things like tracking and things like analyzing patterns. And if you think about all those applications for radar in industry, they are all centered around analyzing those patterns and then tracking things. If you think about your mass media applications of AI, this includes your ChatGPT or things like DALI. These applications are really good at analyzing patterns, and that's why they are able to generate content for people. And also, it's good at tracking things. I'm sure we have all come across those videos on your LinkedIn or social media where people are moving their faces on a video feed and the AI is able to track their faces. And so, really, AI would be well suited to be applied in radar for these reasons. So, AI systems are ideal for radar. But why? So firstly, you get an improved accuracy and precision when using AI for any systems. This is because AI is particularly good at analyzing complex features and relationships within data. And also, this lends itself well to real-time processing as well, because AI is trained on large volumes of data. And so it's specifically tuned to process large volumes of data. And this is especially good for your military sort of applications, whereas traditional algorithms may need to analyze the signal in sort of a step-by-step process, the AI model is already tuned to analyze the large volumes of data. AI systems are also adaptable. So they are adaptable in the sense that you can just retrain a model on new data and can then be expected to perform well on the new data as well. This really speeds up the process. And also, it's adaptable in the sense that they are less sensitive to noise. So they can be applied to a whole host of scenarios without needing to reprogram. Whereas traditional algorithms, you may need to have an algorithm for different scenarios where the noise profile may be a lot different. And so finally, AI systems are also cost effective because you need less people to develop new algorithms for new scenarios. And by being able to actually have your real-time processing, you're also able to save on costs. So I've spoken a bit about AI, but really, what is AI? And so what AI really is, it's any technique that enables machines to mimic human intelligence. So if you think about this, a lot of systems are actually AI. This involves things like your search algorithms, things like your rule-based chatbots, where if statements are used to actually mimic the intelligence of a human being. These all fit the good old-fashioned definition of what artificial intelligence is. But in today's society, people are typically referring to machine learning when speaking about AI. And this is now where statistical methods are used to actually learn tasks from data. So there's no explicit programming required. There are three main clusters of machine learning. This includes your unsupervised learning, your supervised learning, and also your reinforcement learning. What unsupervised learning is analyzing data where there is no input-output relationship of data, but rather you are trying to analyze trends within the data itself and really cluster the data into certain groups. Supervised learning, where now there is an input and output relationship, and you are trying to teach the model to be able to map this relationship. When you give it an input, you get an output from it. And this is the sort of learning we'll cover throughout the rest of this webinar. Then you also have reinforcement learning. This lends itself well to control problems, particularly where now you have a machine learning model, and this model is able to interact with an environment. And from that environment, it gains rewards or gains a penalty based on a certain action that it performs in that environment. And within all these three clusters, you are actually also able to then perform deep learning. And what deep learning is using neural networks to actually build a machine learning model. So although deep learning is a part of machine learning, people typically sort of class them as two separate fields. And so I really want to flesh out the differences between what machine learning and deep learning actually is. So machine learning is where you have raw data and then you perform feature extraction and extract features from that data and then use that to build a model to generate insights. So what feature extraction is, it's a process of breaking your raw data down into more distinguishable aspects and then being able to pass that into your model. So if you think about classifying a bicycle, this would be saying where the positioning of the first wheel is, the positioning of the second wheel, their relative sizes maybe, is there a frame present as well? So if you think about a radar application of that, the features of a radar signal would be things like the wavelength, the period, the amplitude of the signal, right? But of course, you may not always be able to perform feature extraction, particularly if you're not someone who's an expert in the field. And so that's where deep learning can also come in handy. So what deep learning is a method where the feature extraction is actually automated. So you just pass in your raw data and it's able to automate the feature extraction and then generate insights. This is what could be termed your black box models. The next question then becomes, which learning technique is best for your application? There are two metrics to assess this: the domain knowledge and the dataset size or quality. The domain knowledge in this case refers to the domain knowledge about the specific problem. In this case, it would be radar systems. How much domain knowledge do you have about that? So in the case of deep learning, you'd need a very high dataset size or quality because you want to pass in a lot of data so that the model can automatically perform the feature extraction and learn those relationships. Whereas for your machine learning techniques, the dataset size that you'd require is pretty low, but the domain knowledge required is high so that you actually have these features that distinguish between radar signals and are able to tell what a certain signal represents. Somewhere in the middle, you have your pre-processing techniques that allow you to need a little less domain knowledge or a smaller size of data of a data set. And in our demonstration, we'll look at some automated feature extraction techniques, and we'll look at how these play a factor as well. Now, moving on to the AI workflow. It's a four-step process. The first is you want to create and access your data. And once you have this data, you then want to pre-process and transform it because you want to ensure it's of good quality to feed in then to your AI model. Once you build your model, you want to tune it. And once you are happy with the performance of your model, you then want to deploy it. And this is where we really derive the value of the model because now we are using it on production systems. Looking a bit deeper now into some of the steps, in terms of creating and accessing your data, you want to access multiple sources of data. This could be the internet, it could be local files, it could also be databases that you have access to. And if you don't have that data, you want to then create synthetic data. This is especially important for engineering systems where accessing data may be an expensive process in labs and real world systems. So, creating synthetic data in simulation environments is a very viable option to then train machine learning models or AI models in general. You then also want to label your data. This can be a pretty tedious step in the process. So you want to make sure that you plan ahead for it as well. And so in my case, I do all of this within the MathWorks environment. There are various toolboxes addressing each of these steps. You can access multiple data sources and even use your SQL languages, your database languages in MATLAB to access data. You can create synthetic data through things like the Radar toolbox. You can also label data using the labeler apps as well. The next step is then pre-processing and transforming your data. Firstly, you want to perform data cleaning. You want to remove certain aspects of your data. Maybe you want to denoise the signals as well. This could be a form of data cleaning. You then may also want to change the representation of your data. Some signals are hard to distinguish within the time domains. So you want to move to the time frequency domains where you can then leverage some other techniques like your image classification models to distinguish between those signals. You also want to then perform feature extraction. Even for deep learning applications, feature extraction may be performed so that the model just learns faster and can perform additional feature extractions on its own in the black box. And then once you've pre-processed and transformed your data, you want to build your model, and the model can then be built from scratch through various libraries. If you think of Python or in MATLAB, there are inbuilt libraries that contain models, or building a model totally from scratch. And then particularly for deep learning, there's an additional method called transfer learning, where you actually take a model that has been trained by other people on other data and it's of complex architecture. And then you are able to leverage that architecture and really manipulate the last few layers of that model and then have that come through to label your own data. And then once you are happy with your model, you then are able to tune it. So tuning is the process of actually toggling the settings of your model so that it performs better and to the level that you'd actually like it to perform at. So moving along now, I'd like to step into the demonstration. So opening up the MATLAB UI, towards your left here, you have your folder structure where you can see all the files that you have in that specific folder. Towards your right here, you have your workspace where as you run your code, the variables pop up in this workspace, their names and their values. Sometimes their types as well will be shown here. And then you have your command window here where you can write inline code. Towards the top, you have your navigation pane, and one of the things I'd like to show you here is actually the apps pane. And in the apps pane, you have a whole host of apps available from MATLAB. And these apps allow you to interactively design computations, build models, And then you can export that to actual code or to functions as well. So we will use a few of these apps like your classification learner and your deep network designer. You just double click on the app and you'd actually be able to open it. You can also search for a specific app you may be looking for. So opening up the example, then firstly, I'd just like to discuss what this format is. This format is called a live script. It has a .ml extension, and it really combines the power of both scripting and reporting. So you are able to have these markdowns and you are able to adjust the text options that you want for your markdowns, and then also have your code for scripting, and then your outputs are able to also be here in line. So this is very good for technical teams to use when sharing documentation between themselves. You can also have various views for this live script. If you look at this, you can have the outputs towards the right, and then your report and code on the left. You could also have a format where it's in line as earlier, and then you could also have a format where you only have the report and the output. So none of the code is actually showing here. So depending on your need, you could toggle between these. And so another function, when you run code from a live script, you are able to hover over the variables, and we will see as we run some of the code blocks that when you hover over these, you're actually able to see the values of the variables. So the example we are doing today is radar target classification using machine learning and deep learning. This example can be found on the MathWorks MATLAB websites. If you just go online and type AI for radar examples using MATLAB, this will be one of the examples that they do give you. This example uses a simple data set where we have signals that are representing the radar cross-section target returns for a cylinder or a cone, and we are trying to build a model that classifies between those two, um, taking in the input of the signal. So the first step is that we are able to generate synthetic data. So the synthetic data is generated simply using the MATLAB function for a cross section. These functions have their documentation online with MathWorks. So if you want to know what input arguments come in here and what the output arguments are, you can search for that online. And then once we have those outputs, we just plotted it on a surface to show you the power spectrum of that. So those returns from the function, we input them into a backscatter object, and that allows you to create a target object where you can now apply various samples that have various azimuth and elevation angles to then get the target return of that specific cross section. And that's what we do in this line of code, where we get the target returns for 100 samples at different azimuth and elevation angles. So essentially rotating the cylinder around and then getting the radar cross section return for that. And when we plot those target returns, we are able to see what they look like for each of the 100 samples. This would be the target. So this is essentially how all the data was generated for this. We preloaded all the data. And as you see, when I run this block of code, all of that data actually comes through here on the right in our workspace with the names and the values as well. So the data contains 50 cylinders and 50 cones. This comes from the fact that we had 10 different motion profiles and had 5 arbitrary radar for both the cylinder and the cone. And then for our test data, we have 25 cylinders and 25 cones that we will try to classify. We have 701 samples for this data. And then some of these other load functions were used to load some of the pre-trained models that use deep learning to avoid training during the demonstration as well. And so if we plot some of those returns, we are able to see that this is how a cylinder return would look like. This is how a cone return would look like. And then this is a motion profile for the cylinder, a motion profile for the cone as well. So this data set is rather simple, but of course it can get complicated depending on how the cone is orientated to distinguish between the two. But your real world data sets will be a lot more complex, but this workflow will really still apply for for all those sorts of data set. It might just be a lot longer to run and train the models, but the workflow is applicable to all those sorts of problems. And so the first thing we want to do when performing machine learning is, of course, feature extraction. So as it stands, we only have our data that represents the returns from the cylinder, the returns from the cone. So we want to extract the features from that data. And I'm not a radar expert, so we want to use a pre-processing technique that doesn't require a lot of domain knowledge. And in this case, we use wavelet scattering. And what wavelet scattering is in simple terms, it's essentially using wavelets, which are tiny waves that are applied to a certain sample of the signal. So they're applied in a certain bandwidth, and they are either squished or really stretched to capture the high frequency and low frequency data. And then you have different wavelets that you apply to the whole signal over a different band. And then you also apply these wavelets over different filter banks or levels so that you capture more of the rich information of the signal. And this allows you to get coefficients for the signal when the wavelet scattering is applied. And so MATLAB has a function called the wavelet scattering function, and that is able to create an object for wavelet scattering. So that's what you do in this line of code. And in our case, we use 6 wavelets. So we'd have 6 coefficients for that, 4 in the first level, 2 in the second level. And wavelet scattering is really good at excluding the noise from the signal and capturing the actual data. And so when we apply our then returns to the actual object, which is the wavelet scattering object, we are then able to obtain our trained data. So in this case, when we apply it, we can see that as we hover over this, we are able to see all of the trained data that is now present here from the wavelet scattering. And then we compress that a bit so that we only have the features as the samples for where the wavelets are applied. So we use the squeeze and the mean of that. And then you can see here how our trained features look. It's 100 by 162. So the 100 represents the rows of cylinders that we have, and then 162 is the number of features that we have. So that's each bandwidth where the wavelet scattering was obtained, and then the coefficients that were found for each of the wavelets summed over that band. And then we also then finally have our train labels. So as you can see here, we just have 50 cylinder categorical array. And then here we have our test labels as well, where everything was obtained similarly. So now we have our training data for machine learning ready. And so we want to now build a model using machine learning. And you can easily do this in the classification learner app because we want to classify these signals as either being cone or cylinder. And so if I open up the classification learner app, this is how it would look upon opening it. And then if you select a new session, we want to extract data from our workspace where we've actually logged that data. And so when we open this, we are then able to select the input, and we want to use our train features. And then it automatically detects what the response variable would be. So here it selects it from the data set, but we want it from the workspace because we have an array for that, which is the train labels. And as you can see, it automatically detected that. And then here you could also set aside test data from that data you have, but we have a separate variable for test data, so we do not need to do this. But what we are doing here is a cross-validation scheme. We are using 5 folds. What cross-validation is in simple terms, it's keeping a certain portion, usually about 10% of the data. And then when you train the model on that remaining training set of data, you then capture the accuracy using that validation set, and then you put that set back in and you select a different set and train the model again. And so in our case, we'll be doing that 5 times, and then we start the session. And so when you start the session, it's able to create just a dummy model. And so we're not going to need that. And then you can also log the test data. And in our case, it's from the workspace as well. And then here it is our test features that we are logging. And as you can see, it automatically detected that the test labels would be the response. And then we want to import that as well. And then the data is imported. Okay. if we go back to learn, so now there's a whole host of models available here in the Learner app. As you can see, you can also, once you have created your models, see the scatter plots, confusion matrix, the ROC curves, and really export some of that data as well. And so I'd just like to touch on the feature selection as well, because once you have your model, you could be able to select the most important features of that model. And this is where the domain expertise would have to come on. So you are able to apply different types of algorithms here to rank the features. And then if you have the expertise, you could select which features are most important for your application, or actually manually select the features. As you can see here, these are all our 162 features. However, because we performed an automated feature extraction, we wouldn't actually know what these features represent. And because we are not domain experts in that field, we'll just keep all the features here. We could also use parallel to train the model, but in our case, we train it on our CPU. And so if we select all the models that are quick to train, because we want to train all of those, then you can just select train all, and you'll see it's a fast process to actually rapidly develop these models. It's going to develop multiple models here towards the left, and it's going to begin to train them. Luckily, our data set is a bit small, so this training could all actually happen, and you'll be able to see what it looks like. And so the first model has been trained, and you see it's able to output a confusion matrix for me. And what I also want to cover is that you are able to export this. So once all the training is done, we'll be able to export either a figure or export a function to train all these models, or export a certain model specifically. And so as you can see, some of the models here are performing at 100% for your validation accuracy. Some are at 50, some are at 98, like your KNN here. And then all the training is now done. So you see, you can actually export all of this. But first, let's apply the test data as well. So we can test all these models and see which one tests best. So if we test all of them, it's going to be a quick process. So this is the test accuracy. You can see there this KNN has a 50% test accuracy. So if you click on a model itself, you are able to see some of the hyperparameters of that model and see what those hyperparameters are. It tells you that it used all 162 features. And so if we go back to learn here, as I said, you are able to export a model either to your workspace and just use it in your workspace or within your functions, or even save it to a folder. You are also able to export your model for deployment to production environments if you are happy with the performance, or you are able to export this to Simulink if you are using it within a Simulink model, or you are also able to create an experiment. And what an experiment is where you could actually tune some of those hyperparameters of your model so that it could actually perform better, particularly on your test data. So just looking at the experiment manager, actually. So in the experiment manager, you are able to log the model that you are trying to train. So you will export that model to a function and have that present in a function. So in this case, it's experiment 2 training. And so once you have that model in a function, you are able to specify which hyperparameters you want to tune for and the range of these hyperparameters. So MATLAB documentation could actually help you establish what those ranges are. And then you select a strategy for your hyperparameter tuning and either an exhaustive sweep. In this case, I used a Bayesian optimization. And if you go to the results, then it's able to then generate a, a host of models which use a lot of combinations of these hyperparameters to actually establish what is the validation accuracy for all, and then select the best model for you. So in this case, the fifth model was the best performing model. And then once again, you are able to export this with all its values. So in this case, you would have trained a model and found the best values for that model. So going back to MATLAB now, this is the process we do here programmatically. We create a template SVM, and so we set all the values for that SVM, which is the support vector machine. So in this case, these values would have been found from your actual experiment manager after tuning your hyperparameters. And then we finally create a classification support vector machine. And then we use that classification vector machine to cross-validate and find out what our validation accuracy is. And in this case, the validation accuracy is actually 100%. So our model is pretty well trained, and now we want to see how it performs on the test data. And when we run it now on the test data, we see that it actually just has an accuracy of 84%. And so when we plot the confusion matrix for this test set, we can see this is how the confusion chart looks. Hopefully it's not too confusing. I look to explain it here. So how you read this is that all these rows represent the cone, all these rows represent the cylinder. These columns here are the cone, these columns here are the cylinder. So firstly, analyzing all the misclassifications is that remembering that there's only 25 cones and 25 cylinders that we have in our test set. So this confusion chart tells us of the 25 cones, 17 are predicted correctly as cones, while 8 are misclassified, which means this 8 are predicted to be a cylinder. So this is where now these percentages come from. 68% of the cones are correctly classified, whereas 32% are incorrectly classified. For our cylinders, then, we also have that 25 of our cylinders were correctly classified. So there's 100% accuracy for classifying our cylinders. And then when we look at our predicted class quadrant here, so this whole column represents cones, this whole column represents cylinders. So what this tells us is that when the model predicts a cone, 100% of the time it is correct because there is no misclassification where you have a cylinder being predicted as a cone. So all 17 cones were identified as cones, and that means it has 100% predicted class accuracy for predicting cones. But if you look at our cylinders, although all our cylinders are classified correctly, but there are some cones that are classified as cylinders. So this tells us that when the model predicts a cylinder, it's sometimes not a cylinder, and that happens 24.2% of the time, where it predicts that something is a cylinder, whereas it's actually a cone. And so you see this by this misclassification of cones. And so that's how you'd read your confusion matrix. And so now we want to move on then to transfer learning using deep learning. So we want to approach this problem from the lens of deep learning because now we can see that the accuracy using machine learning in this case is 84%. And so I'd like to just move to the deep network designer. So we are going to use a image classification model called the SqueezeNet. So the SqueezeNet has a relatively complex architecture. So each block here represents the layers of the SqueezeNet, and to the left, as you are designing your own neural network or adapting a neural network that you already were able to import, you could actually add more layers, remove certain layers here. This is the deep network design, and you are also able to export the model here as well. So if we just zoom in to some of this data we have here on the SqueezeNet. Okay, there we go. If we just look up, like I said, it classifies images. So this would be the size of the image that it takes in. And then once it takes in that image, it passes it through all these layers to then classify it into a certain number of classes. So we want to modify, as I mentioned earlier in transfer learning, the last few layers to fit our problem. So in our problem, we are trying to classify two things, but SqueezeNet is actually created to classify 1,000 images, right? So these last few layers, as you could see, these are not learnable layers where any learning takes place, but rather it's scaling layers. And so we want to unlock this layer and change it because we only want to classify two things. And so when we change that, we then see that we have two layers, two classifications. And then we also want to change some of our learn rates because learn rates are basically the step size you are taking to perform the training. And so we want to take bigger step sizes because our data set is a bit more is a bit less complicated, right? So we want to take bigger step sizes, and you could also find documentation regarding the learn rates on MATLAB as well. But think of it as a step size you take during training to see how quickly you could converge. So if you think of training as over an entire surface, you don't want to take a training step that's too big because then you may miss the actual minimas that you are trying to converge onto, and you don't want to take steps that are too small because the training may take a very long time to do this. So once we've adapted this layer now to fit our problem, we can actually analyze the network for any errors. And so this is able to show you a condensed structure of the network and then tell you if there are any errors with your setup of your problem. And so in our case, shouldn't expect any errors. Yes, there are no errors as you can see. And then we have the condensed structure here towards the left. And then you can see some of the layers that we have here. As I said, there are 68 layers. There are 68. And the last layer that we changed was this conv layer, which was the 64th layer. Okay, and so once you have this, you could then export your model as well to the workspace or to a function. You could generate code for this, export it to Simulink as well. And so if I just go back to our code here, we actually import the SqueezeNet here as well, which classifies images. And so you can see that the first layer shows you the size of the image that it's supposed to take in. And so the question then is obviously, we are trying to classify signals, not images, but you could really transform a signal to a representation that can be considered an image, such as your time frequency map. So we're going to look into that, but in my command window, I just want to run a code that just selects one of the signals here so we can use it within other applications to just show you what you could do with MATLAB. Okay, so in our Signal Analyzer app, this is the Signal Analyzer app, a pretty simple UI. You are able to load signals from your workspace. And so I've created the signal. I load it now here, and then you have the signal. And so you could actually analyze the signal and do a lot of pre-processing. So when you are in pre-process, you are actually able to apply some filters. You're able to clean your signal depending on how complex it is. You could convert it. You could also add a custom function to your signal if you want to do something specific to your signal. And once you are done with that, you'd accept the changes. So we aren't doing any pre-processing here. However, we do want to look at how we could display our signals differently so that we could actually leverage the SqueezeNet, right? So if we use a time frequency map and obtain a spectrogram, you can see that we have our spectrogram here. And so we want to be able to distinguish between the cones and the cylinders, but you can see that it's hard to distinguish between some of these high frequency bands here in this spectrogram. So we may want to use a scaleogram. Maybe it's easier to distinguish. And indeed, you can see the bands are a bit easier to distinguish, but let's say you wanted to further alter your scaleogram to even give you a better result. So this is where now you'd use another application, which is the wavelet time frequency analyzer. You could import signals as well to the wavelet time frequency analyzer. And so because we have a signal in our workspace, we import that. And once we are done with that, it's going to come up. Okay, here's our scaleogram. So maybe let's say you are not happy with how this looks. Now you have a lot more functionality in the wavelet time frequency analyzer to actually adapt your scaleogram. So let's say we want to use a different wavelet, a bump wavelet in this case. We want to change the number of voices per octave, and then we see how that changes the scaleogram to actually be better. If we compute that scaleogram, we can see now the bands are a lot easier to distinguish. So if we just made this an image and passed this into SqueezeNet, it would be easier for SqueezeNet to actually separate between the cones and cylinders using the image of these scalograms. And that's what we're doing in this actual problem. And so programmatically, we do this. We are able to create with the function through MATLAB CWT, we are able to create a continuous wavelet transform on our signal, and then we can see how that would look like. And so once we get the target returns as well for a cylinder, and we show the aspect angles using the continuous wavelet transform, we see how that looks. So now we want to transform then all our returns, which is the RSC returns and our test returns, into these images. And that's what this segment of code does for us. And once we have this, we want to then store this into a management system called a data store, which creates a function of a folder. And gives it object qualities. So when you create a data store from a folder, you are able to use those folder names as actually labels, and it doesn't commit any of the files to memory, so it makes it easier to process using a data store, right? So this is a function that is recent to MATLAB, so you may want to use this a lot more often for your workflows. And here programmatically, we are doing what I was doing in the deep network and designer, where now you changed the learn rates for the squeeze net, and then you change the 64th layer as well, which was the last learnable layer that we spoke about. So from the deep network analyzer, actually, you are able to bring this code in, or you could do it from scratch in the code formats, but it's good for beginners to use the apps and just get a feel for things. And then finally, you are able to set your training options. So these training options, you could find documentation for it as well on MATLAB, what learn rates are, what maximum number of epochs are, and batch sizes are. But you could also select their values using the experiment manager. So you could sweep through a whole host of ranges for each of these values and combinations, and even for the optimizers that you want to use, the algorithms. So you sweep through all of that, and then once you find which one performs best, you export those values for it. And so we set training options here for the model. And then once we set those training options, we want to train the network. So we just pass in the training data, the actual squeeze net. So this is the adapted squeeze net now. It's called L graph squeeze here. And then you pass in the training options, which you could have found through the experiment manager. And so we aren't performing training, but when you do, the training occurs such that it creates a pop-up. And in this pop-up, you're able to see your loss function, which you want to minimize. It's the difference between your expected output and the output that you are actually getting. So you want to minimize that. You want to maximize the accuracy. And so it tells you some information here in this training progress pop-up, how long training took. And also you could export this as an image if you are reporting or preparing a presentation about how you performed the training. And so we skip that step. And then we are, however, using now our continuous wavelet transform network to predict based on our test data. And we can see that the accuracy for that now is 100%. Remember that earlier our machine learning performed to 84% accuracy, but now you can see here using deep learning, especially on a data set that is a lot smaller than traditional data sets that you'd find in the real world applications, you can see that the accuracy is very good here. And so if we plot the confusion matrix, then this is how a confusion matrix for 100% accuracy would look. So you can see here, there's no misclassifications, there's 100% accuracy, there's 100% predicted class accuracy as well. And so you could also then create your own neural network from scratch. And that's basically what is being done in this last block of code. So what happens here is that these layers are created, and you can also do this interactively as well, remember, using the applications, but you create the layers, and once you create the layers, you specify the training options as well. And then here we are using the actual training signals to process. So you can see here we have our actual signals. So this is the signal data that we'd have, and we are not using an image for the long short transform that we built here. And so once we train that as well, the training would look like this. The pop-up would happen, and you want to minimize your loss, maximize your accuracy, obviously. And then when we are able to generate predictions off of that, we can see that the accuracy here is also at 100%. So in conclusion, you can see the difference in performance you can get from machine learning and deep learning. And actually the key point here was to just highlight the workflows of how you'd build a transfer learning model, how you'd build a model from scratch, how you'd build a machine learning model, how you'd pre-process. And so this example really covers all the steps. And like I said, it's available on MATLAB online. So if you just Google AI for radar in MATLAB, you can find this example and get deeper into understanding it, because this workflow is the typical workflow you'd follow for any machine learning problem. And so that's it now for our demonstration. I'll be moving back to the presentation now. time to discuss the true value of what these AI models would be, and that would be bringing the systems into production, and that is done through deployment. So MATLAB has a host of options available to users to deploy the AI models. Firstly, we have the coder products, and what the coder products allow you to do is deploy your AI models onto embedded hardware. So you are able to transform your MATLAB code into programmable logic controllers for CUDA code or into C and C++ code, and this can then easily be integrated onto your embedded hardware. We also have the compiler options where MATLAB allows you to deploy a model as a standalone executable. You could deploy to web apps, which is also a MATLAB functionality. MATLAB has a web app server available. You could deploy onto Docker containers where you could then use these Docker images on other sorts of hardware or deploy to servers and such. You also have then your compiler software development kits. And in your software development kits, you are actually able to transform MATLAB code such that it can be compatible with various languages applications infrastructure. So you could transform your MATLAB code onto Java classes so that it could be used within a Java application, or you could transform your MATLAB code into Python modules or .NET assemblies, which can be used in an application that uses that sort of infrastructure. You also have the option to develop your code and then deploy it onto your production server environments. This could be within MATLAB. MATLAB does offer a MATLAB production server environment, or it could be within any other sort of production server environment. But the key is that MATLAB allows you to easily integrate your own AI model into these systems. And of course, there's a compiler for Simulink as well. If you are developing code that you want to use within a Simulink model, in the case of model-based design, you could do that as well. And this is really where you would see the value of developing AI models is by deploying them on these systems, but also the value of MATLAB because it so easily provides you with the infrastructure to integrate your code into various sort of forms. And so that brings us to the end of the webinar. If you do have any questions, please do not hesitate to reach out to me. I am Talukolo Hatebe once again at optinum.co.za. This is my email, and it's been a pleasure hosting this webinar for you. And I hope we all were able to learn something, and in the future, we could all apply AI to whatever workflows we are working in terms of be it your radar systems or any other systems as well. Let's have a chat. Thank you.